Today, I presented a homework problem to the board in my Fourier Analysis class. The reason I've decided to make a video about this particular problem is because if you remember in my previous videos, the way we get graded in that class is we present problems at the board, and then for successfully proving the result, we get credit. And if you solve 4 problems, then you are finished for the semester. And this homework problem, was number 4 for me, which made me feel pretty good. And more so, the problem that I presented at the board, I really liked, because most of the time when my instructor gives me a homework problem, most of the time I'm looking up stuff on the internet. I may not copy it directly, but I have to do a lot of digging myself and, reading in various textbooks. Like, I haven't really used this book too much. I noticed it here in the corner, Fourier series. But I like the Katznelson book, which is currently in my backpack. I don't feel like getting it out. I did consult this book just a tiny bit to do this homework problem, but it didn't really prove to be useful. It makes some comments about Fourier transform that I wanted to check, but it didn't help me. But I was curious to see if something in there was useful. So in this video, I want to talk about a few things, but I thought I would start by doing the homework problem that was given to us. And it's a measure theory problem. It's not really related to Fourier. Well, I mean, it is related to Fourier analysis, but it was more like a result that we needed to establish a bigger result. And rather than just show us, the proof of this, I couldn't think of the word. He just said, you do it for homework. See what you can come up with. So he gave us this problem on Tuesday. I went home, I thought about it, and I was kind of taken with it. I read it, and I was like, I bet I could do this. Because it's all measure theory. And I've been practicing my measure theory for like 2 years now to pass that qualifier back in the summer. And part of the reason I was so happy about this problem is because I was able to look at it, read it, and maybe not in 10 minutes, but at most 30 minutes, I was able to digest the problem and come up with a solution. So it kind of serves as like a benchmark for my ability in understanding these measure theory problems, because 5 years ago, there's no way I would have been able to do this problem. And maybe even as recent as 2 years ago, I probably wouldn't have been able to do it. Because for those people that watch my channel that are still like in high school or maybe early college, I would say of all the math classes I've taken, I would say measure theory is probably the hardest math for me, definitely for me, and maybe on average for most people, because I haven't taken every single math class, but there's just something about measure theory that makes it slows people down. They got to go through it slowly, and I didn't really understand it until like I took it the first time, and then I took it a second time. I passed both times, but I was forced to take it twice when I entered the PhD program. And then I read all those books, but I've kind of beat that dead horse, so I'm not going to go through it again. But this served as like a benchmark. It proved to me that I actually did learn something, because I was able to look at this and go, okay, I know how to do it, and boom. 30 minutes, it was done. So what is the problem, if you haven't read it? Fn is a function that maps real numbers to complex numbers. It is continuous for every n. We assume that it is square integrable, which means that if you take the integral of this over the whole space, r, and then take the absolute value of it, square it. Well, I should say that first. Take absolute value, square, and then integrate. It's finite for every n. We say that Fn converges uniformly to G on R, and Fn converges to H in the L2 sense, which means that you take the absolute value of this minus that, and then take the integral, and then pass the limit through, or take the limit of it, and it tends to 0. We want to prove that G is equal to H almost everywhere on R, which means that these two functions are basically the same up to a set of measure 0. Which means they only differ on a set of measure 0. And for those people that are like maybe in Calc 1 or something like that, you'll look at this and go, oh my gosh, this is horribly difficult. And then for other people that have taken analysis and working on their PhDs, you probably look at this and roll your eyes a little bit. But it's all relative, you know. 5 years ago, no way, couldn't do it. But now I can do a problem like this in 30 minutes. So let's do it. So my original inclination of when I was thinking about this problem, so I'll go through my thought process a little bit about reading this and what should I do. I remember reading something in the Stein book where if you want to show something has, you know, two functions agree almost everywhere, you look at a set of where they differ. You know, so if G is equal to H almost everywhere, then we want to show that this set E that I've defined has measure 0. But you can't do it directly, you have to do it in pieces. So I defined E alpha to be the set of all absolute value G minus H bigger than alpha for fixed alpha positive. And the idea here now is to rewrite E as the union from k equal 1 to infinity of E sub 1 over k. And then, you know from countable subadditivity that the measure of E has to be bounded above by the sum of measure of E 1 over k, where k runs from 1 to infinity. And if you can show that the measure of E alpha is 0 for any fixed alpha, then you know that the measure of E of 1 over k is 0, and the countable sum of zeros is 0, in which case the measure of E would be 0. So that was my idea. This is what I wanted to do. If I can just show that the measure of E alpha is 0, I was done. But when I was presenting it up at the board, I recognized that there was a snag. And I'm pretty sure that what I was doing was all correct, but I wasn't sure how to fix the snag. So as I was up at the board, I was thinking a little bit about how to fix it, and then a friend of mine in the class, he might actually watch this video, he knows about my YouTube channel, he suggested I do something. And what he suggested was really brilliant. So what do we need to do? And the fix occurs here. So what we want to do is define a new set. There's a lot of sets here called E sub, I should put alpha first, but it doesn't matter. En alpha to be E alpha intersected with the interval from negative n to n, where n is just any real number, but it can be an integer, it doesn't matter. Because then, if you show that this set has measure 0, then we recognize that E alpha can be written as the union, countable union, from n equal 1 to infinity of E n comma alpha. So again, by countable subadditivity, we would have that the measure of E alpha is bounded above by some measure E in alpha, n from 1 to infinity. And so if you can just show that this set has arbitrarily small positive measure or non-negative measure, then you're done. Because this would be arbitrarily small, and this set, I don't know what I'm looking at, can be written as this union, so that this is arbitrarily small. So then you're done. The measure of E would be arbitrarily small. So the whole proof relies on this claim. The measure of E in alpha is 0. If you can show this, you're done. Okay, so let's do it. So what was my thought when I tried just doing it with E alpha and I ran into the snag? And I would point out the snag when I get to it. But if you just think of this as E alpha here, so what was going through my mind about how to show that this is 0? I was trying to think of all the types of bounds that you can get on sets or measures of sets. And the first thing I thought of, because I know that I need to use L2 in some way, I need to introduce an integral. And the only bound that came to mind at the moment was Chebyshev's inequality. So Chebyshev's inequality It's actually the inequality that appears on the front cover of this book from earlier. This guy, that's Chebyshev in some form. Chebyshev says the following: the measure of E in alpha is bounded above by 1 divided by alpha squared times the integral of E in alpha the integral of what function? G minus H, right? My voice is cracking awful in this video. I guess I really do have a nerd voice, don't I? That didn't really bother me the other day. There was a video on my channel that blew up like a week or so ago. No, it's been longer than a week. I did homework at the PhD level, and someone commented on that video that I had a nerd voice. And I pinned it because I thought it'd be funny to pin it. And lo and behold, that video ended up getting like 200,000 views or something. I have no idea why. There's no reason for that video to be as popular as it was. But whatever. So now what do we need to do? We need to somehow send this integral. We need to make this integral small because alpha is fixed, right? So this is just some constant that hangs out front. So we need to make sure we can send this to 0 somehow. And what we do is we use some form of the triangle inequality. So you have G minus H squared. I add 0 inside in a creative way. So this is my creative way. And now you can split into 2 pieces. So you have Fn minus G squared plus H minus, well, I like F first, but it doesn't matter. But I'm lying here because you can split this way, but it's only bounded above by this sum up to a constant, and that constant is 2. And this was my first mistake when I wrote it up the first time. I forgot about that 2, but I was pretty sure it was true because I saw it in the proof of Minkowski's inequality. So if we replace this 2 up top with a p, then it becomes 2 to the p minus 1. But here p is 2, so it's just 2 out front. But it doesn't matter, 2 is just a constant. And so now what we can do is do this substitution. So we end up with measure E in alpha is bounded above by 2 over alpha squared, integral E in alpha. And what I'm going to do is combine 2 steps and just write this as Fn minus G, quantity squared dm, plus integral E in alpha Fn minus H, quantity squared dm. Close the parenthesis. Okay, so now what? You want to pass the limit through. So you want to take the limit as n tends toward infinity on both sides. But this side is independent of little n. Big N makes no difference here. We're really looking at the limit as n tends toward infinity, little n. So this side is independent of n. It doesn't matter. This is just a constant. Who cares? This guy, when you pass the limit through, tends to 0 as n tends toward infinity, because Fn tends to h in the L2 norm. That's where this property comes into play. So since that converges to that in L2, this integral disappears. The snag that I mentioned earlier occurred here, because when I originally wrote this up, there was no capital N here. And then we just had to set E alpha. There is a theorem in the Whedon book called uniform convergence theorem. I don't know if other textbooks really have a name for it, but what the result says is that under some conditions, you can pass the limit through if you have uniform convergence. And in this case, we have uniform convergence here. Fn converges uniformly to G. So for that logic, you can pass the limit inside. But actually, to do that, you need to know that the space that you integrate over has finite measure. And I did not know that E in alpha, or excuse me, in this case it'd be just E alpha. I did not know if that set had finite measure or not. It could have had infinite measure, in which case I'd be screwed. But, so that was the part that I was trying to figure out. Maybe I could decompose E alpha in some way, but it wasn't making sense to me. But my friend's suggestion to introduce this guy, this trick, that measure theorists often employ, shows that En alpha is a subset of this interval which has finite Lebesgue measure, and that E alpha can be written as the union of those En alphas. So by showing that this has set measures, or this measure has, that this set has measure 0, or these guys, you can get this bound, in which case this set would be bounded above by 0. I keep saying the word bounded a lot. But that's essentially what we need to do. So let me get out another sheet of paper. I'd hate to rip this off, but I guess I don't have a choice. Okay. So I wrote this up at the board. I don't really think it makes much difference because I don't really see where continuity came into play. But Fn converges uniformly to G. Fn is continuous. So together, this means that G is continuous, which means that Fn minus G is itself a continuous function. And we know that Fn minus G must converge uniformly to 0 on En alpha. Really on the whole space, but I only need it on En alpha. So we may pass the limit through. Pass the limit inside the integral. So what this means that I take the limit integral En alpha absolute value Fn minus G quantity squared. The squared makes no difference in this case. You can think of it as a function in and of itself. So you're composing a continuous function inside a continuous function. So we end up getting integral En alpha past the limit inside Fn minus G squared dm, and this guy tends to 0, which means that we integrate 0 over this whole thing, so we end up with 0. And then we get the claim. Hence, measure En alpha is 0. That's all we wanted to do. So yeah, I was pretty proud of myself that I was able to come up with this, because it shows that I actually learned something. You know, because this stuff was very difficult for me in the very beginning. I mean, it's just, like I said, it's calculus on steroids. And hopefully I'll be able to keep up with this. You know, I've been thinking a lot about what I want to do after I get my PhD, whether I want to just get a teaching job or try and get a job working in maybe finance or something. I should have this stuff figured out by now, but I don't. And I guess if you're still in college or about to go into college, I guess my biggest piece of advice is to figure out, I mean, don't rush yourself, but also, you know, think actively about where you want to be in 5-10 years. You know, that 5-year plan or whatever that everyone keeps talking about. You just don't want to be perpetually in school forever. But anyway, let's just work on the PhD at first. As far as research goes, if you're interested, I've been trying to do research, but I've been unsuccessful in it. I've been looking around at different but graduate advisors. I've had some luck, but mostly no luck. It's it's a complicated situation. In the video's been 19 minutes so far, so I don't want to drone on and on and on. I really just want to stay in my comfort zone and do some sort of research with Cantor sets and fractal geometry, because that's what I did my thesis and my paper on, but it sounds to me like I'm going to be forced to do something else, which is fine. I'm not complaining about it. It's just, it would have been easier for me to do something in the stuff that I've already been, you know, writing about. But I'm just glad that I'm still here. I passed that qual and I can move on. Hopefully in 2 years I'll be done. If not 2 years, then 3. Or maybe a good job will come by and I'll just leave. Because I am kind of at that stage where I don't want to be in school anymore. Anyway, I hope you enjoyed this problem. I really like this problem. And I hope it made sense that I explained. I kind of went through it fast, but that's just because I'm too excited.